Let's dive right into an amazing engineering development story today. If you're an engineering student, or honestly, just someone fascinated by the process of taking a completely blank canvas and turning it into a real, functional device, this explainer is exactly what you've been looking for. We're going to walk step by step through the design, simulation, and real-world validation of a high-gain Electret microphone preamplifier. It's all about transforming pure theory into practical signal conditioning. Here's our roadmap for the journey. We'll start with the preamplifier design challenge, move into step-by-step component selection, jump right into validating with LTspice analysis, break down the signal-to-noise and distortion, and finally, go from simulation to physical hardware. All right, step 1, the preamplifier design challenge. This step-by-step blueprint is our rigorous methodology. It's a perfect framework for engineering students who want to bridge that gap between theoretical circuit design and practical implementation. We're going straight from analyzing what the circuit absolutely needs to do, all the way to benchmarking its actual performance against our original goals. So, the crucial point we have to tackle is the functional requirement. Electret microphones are fantastic for mid to high frequencies, but they output this tiny, sometimes really noisy signal. Our job? We must amplify that low-level audio input into a clean, robust 2.5-volt peak-to-peak line-level signal. And we have to pull this off across the entire human hearing range, from 20 Hz to 20 kHz, without losing a shred of fidelity. It's no small task. Okay, moving on to part 2. Step-by-step component selection. The first major choice we face in our circuit topology is the amplifier configuration itself. We went with the non-inverting amplifier topology. Now, why is that? Well, an Electret microphone actually includes a built-in field effect transistor, or FET buffer. Setting this up as non-inverting preserves the phase of the audio and maximizes the input impedance. Essentially, it isolates the microphone source from the rest of the circuit, which prevents any unwanted loading effects that could completely ruin our audio before we even amplify it. Now, this is where it gets really interesting, the precise why behind each component. If you're an engineering student, you already know component selection is where you make or break the entire design. We're using a bias resistor between 2 and 10 kiloohms to properly bias the microphone. Then we implement specific 1 microfarad and 2.7 microfarad coupling capacitors. These are absolutely vital because they act as high-pass filters. They basically block out unwanted direct current, or DC signals, from sneaking into the amplifier or the next audio stage. And finally, the heart of the whole setup, the TL971 IDR operational amplifier. We picked this specifically for its incredibly low noise, its rail-to-rail output, and a super low quiescent current draw. To hit our target of a 2.5-volt output, we've got to scale that input up dramatically. By carefully calculating our feedback resistors within that non-inverting topology, we aimed for a very specific voltage gain multiplier, exactly 357 times the original input. Up next, Section 3, Validating with LTspice Analysis. This perfectly illustrates the amplifier doing the heavy lifting in our simulation software. We essentially fed this simulated circuit a tiny 0.05-volt peak input using a pure 1 kHz sine wave. And sure enough, LTspice confirmed that our circuit transforms that weak little input right into our robust 2.5-volt peak-to-peak target output. Seeing that is just a massive validation of the math behind the design. But hey, we didn't just stop at checking the voltage. We put this circuit through the ringer with multiple rigorous simulation phases in LTspice. We ran an AC sweep analysis just to ensure we maintained a perfectly flat gain across the entire 20 Hz to 20 kHz audio spectrum. Then a transient analysis to verify the time domain response, making sure the integrity of the waveform stayed intact. And finally, a power analysis to strictly track exactly how much current we were drawing. Let's look at Section 4. Signal to noise and distortion. Noise analysis in LTspice is absolutely critical for a project like this. By comparing the output signal's root mean square, or RMS value, against the integrated spectral noise density, we were able to prove that our design actively cleans the audio input. We're talking about a massive signal-to-noise ratio of 95 decibels or higher. Put simply, the actual audio signal is overwhelmingly louder and clearer than any background electrical noise. And going beyond just the baseline noise, we took a hard look at the total harmonic distortion, or THD, using a fast Fourier transform in our transient simulation. The results? They confirmed our audio stays crystal clear.
The highest, most problematic harmonic distortions were kept greater than 45 decibels below our fundamental frequency. Plus, the bandpass response was completely consistent. Basically, we designed a circuit that cranks up the signal while completely burying the noise.
So, the simulation looks flawless. But as any engineering student quickly learns, theory and reality, yeah, they can sometimes clash. Now it's time for the ultimate climax of our development story, taking this perfect digital theory and translating it into physical, production-ready hardware. Will it survive the real-world test?
That brings us to Section 5, From Simulation to Hardware. We pulled real-world quotes from major component suppliers to put together our complete bill of materials. Looking at the breakdown, the biggest expense by far is that highly specialized LSK170A JFET MOSFET, coming in at just over $10. But looking at the whole picture, this proves that premium, low-noise signal conditioning is totally achievable for a highly economical $13.27. I mean, that is an incredibly cost-effective piece of hardware. And remember that power analysis we ran earlier in LTspice? Well, in the physical prototype, it translated flawlessly. Because our entire circuit, and that includes the microphone, draws an average current of less than 2 milliamps, a standard coin cell battery will keep this hardware running efficiently for over 600 hours. That's a huge win. We've actually done it. We've walked through the entire life cycle. We nailed our frequency response, our voltage gain, our distortion limits, and those battery life goals. This entire story really proves the absolute necessity of empirical validation and meticulous component selection when it comes to electrical circuit design. You don't just guess, right? You simulate, you refine, and then you build.
Armed with this step-by-step methodology, from requirement analysis all the way to physical benchmarking, the real question is how you are going to apply these techniques to your own projects. We've bridged the gap from a theoretical LTspice file to a highly efficient $13 physical prototype. So, what complex circuit will you simulate and build next?